All right, now that we know how an input difference is affected by each layer of the present block cipher, now we can see how we can theoretically obtain a differential characteristic, and then we will talk about how we can experimentally verify the correctness of this distinguisher. So let's look at Wang's characteristics. So for instance, for a 4-round iterative characteristic of present, Wang introduces as follows. So they say that just give 2-bit input differences, namely look at the S boxes 0 and 3 and introduce the input difference 4. So let's go back and understand what is going on. So this is present. So they say that just take a plain text, it doesn't matter, it might be a random value, but then take it again and this time replace the bits corresponding to S0 as the 4, so you just flip this bit, and also corresponding to S3, flip this bit. So your I is something random, let's say, and I prime is just I with these 2 bits flipped. So question is, if their input difference to these 2 S boxes are 4, what can be the output difference? So Wang says that he's going to focus only on the case where the output differences are 5. Okay, so if you go back to DDT table, let's see if it is possible. So for the input difference 4, the output difference is 5, is observed with probability 4/16, which is 2 to the minus 2. But this is probability for a single S box. So we assume that these 2 S boxes are independent, since we independently give the difference and the input was somewhat random. So the probability of both S boxes are having the output 5 has probability 2 to the minus 2 multiplied by 2 to the minus 2, which is 2 to the minus 4. So this is why here in their distinguisher, they say that if the input of these 2 S boxes are 4 and the other remaining S boxes has no input difference, so the input difference is 0, so their output differences are the same. So we are only focusing on active S boxes. So when this input is 4 of an S box, the output is 5 with probability 2 to the minus 2. Same for this S box, so this happens with 2 to the minus 4. Then we apply the permutation layer for the round 1, and these 2 differences due to the permutation layer are sent to some other places. For instance, it is observed that now this difference is sent so that in the following round, the input differences of the S boxes X0, 0 and 8 would be 9. So now they say that let's look at what happens when the input difference is 9. They look at the DDT table and they choose one of the highest probability events, but also with the one which has a small number of bits that are affected. So like 4, which is just a single bit of difference. So again, if we go back to DDT table, we will see that input difference 9 provides output difference 4 with probability 4/16, same like the previous one. So again, this is the case. Now the permutation layer sends these differences to 8 S box and 10 S box with the input difference 1. And the input difference 1, again, due to DDT, provides 9 with this probability. Only difference is here, as you can see, they check when the input difference 5 provides 1. So if you go back to the DDT table, input difference 5 provides output difference 1 with probability 2/16, which is 2 to the minus 3. But since we have 2 S boxes, again, we assume that things happening independently. This happens with probability 2 to the minus 3. This happens with probability 2 to the minus 3. So this is why we observe 2 to the minus 6. So after the permutation layer, now the differences are sent to S boxes 0 and 3. But as you can see, now we return back to our initial case. This is why actually we say this is an iterative characteristic. So let's only first look at the 4-round version. If we assume that these probabilities are independent, then the 4-round characteristic holds with probability of these multiplications, which is 2 to the minus 18. So we assume that all of these rounds are somewhat independent, actually, which is not correct, but in practice, this assumption works. So if we make an independence assumption, the probability of the whole event is just the probabilities of this multiplication of these probabilities, which is 2 to the minus 18. So this means that take a random input I, then give it a difference like this. After 4 rounds of present encryption, the output difference will be this with probability 2 to the minus 18. So this is what this characteristic says. So now important question is, how can we obtain this probability in practice? Because this is just a theoretical assumption. Because in practice, it might be significantly smaller or larger than 2 to the minus 18 due to many different cases. So there might be other differentials starting with the same input, following different trail, but going to the same output. So this probability might be way higher than this. But sometimes this independence assumption might be wrong, and so the probability might be lower. So input and output differences are the same. This is why I called it an iterative 4-round characteristic. So we can put the same characteristic below to obtain 8-round characteristic with probability 2 to the minus 36, hence the name iterative. So take this picture, put it below it. So this time, instead of 4-round characteristic, you have an 8-round characteristic, but this time the probability is just squared, so it is 2 to the minus 36. So you can keep going in this way, but the probabilities at some point would be higher than 2 to the minus 64, but since the block size is 64 bits, going higher than this probability makes not much sense. So let's look at the distinguishing attack. Once you have this distinguisher, this characteristic is actually a distinguisher for 4-round present. It holds with probability 2 to the minus 18 for 4-round present, but for a random permutation, it holds with probability 2 to the minus 64, because this is the block size and you are explicitly saying that this should be the output difference. So you are fixing 64 bits. This is why for a random permutation, this probability is really small. So if we check this distinguisher using n plain text, as you can see, we are turning into a Bernoulli trial, so turning into a binomial distribution. Then we will be trying to distinguish 2 random variables, which are binomial distributions, which parameters P0 and P1. So P0 is the present, P for the random permutation. Recall that the expected values are now n times P and n times P0. So question is now, what should be the n? Of course, it should be higher than 2 to the 18, so that this expected value is higher than 1. So this is what our second homework will be about. It is experimentally verifying a theoretical probability. So let alpha denote our input difference, which is just the input difference to 0th and 3rd S box as the 4 in hexadecimal notation. And B denote the output difference, but it is the same since it is an iterative characteristic. So in this example, alpha equals to beta. Again, this is because we are working on an iterative characteristic. Now, you need to perform experiments, but since we cannot perform this experiment for every key, we will do it for instance, 100 keys. Or if you have the computational power, you can do it for 1,000 keys and so on. But just say that you randomly generated 100 keys. Initialize 100 counters to 0, all of them referring to these keys. So randomly generate n plain text PI. Perform 4-round encryptions for one of these 100 keys on PI and PI XOR alpha. Increase the counter of this key if the XOR of these outputs are better. So calculate the average of CIs and obtain the practical probability of the characteristic, right? So by average, I mean, if you are performing this experiment for n plain text, you have to divide your counter by n to see the average value, right? So that will be your practical probability of the characteristic. So of course, since you are performing this experiment for 100 keys, you will have 100 counters. Just sum all of them up and divide it by 100, and that will give you a somewhat an experimental value of the practical probability of your characteristic. So you might see that this is not hard as long as you have the encryption algorithm, which was your first homework. So it is just a for loop with the I starting from 1 to 100. So you have 100 random keys. And in your second for loop, you have n plaintext. Of course, you might change the places of the for loop. So for every plaintext, you might perform the encryption for 100 keys. And you might increase their counter when you observe this value. So for this reason, you don't even need to store the n plaintext. You might randomly generate them, and once the operation is over, you can throw them out. So this way, you can practically verify theoretical probability. But of course, note that n should be larger than 2 to the 18, because the probability is 2 to the minus 18, theoretical probability. Again, note that this experiment is actually a binomial distribution with p equals to 2 to the minus 18. So just perform your experiment and see how it is, how much it is bigger or smaller than 2 to the minus 18. It might be even the same, but this way we might compare practice with theory.